Have you ever really stopped to think about what's happening under the hood of your car? I mean, it's not just a bunch of mechanical parts anymore. It's a full-on, high-speed conversation between dozens of tiny computers. But here's the catch. This conversation is happening right in the middle of an electrical battlefield, a place just filled with noise that's trying to scramble every single message. So how do engineers make sure that those critical commands actually get through all that chaos? Well, let's dive in and find out. See, your car is an unbelievably hostile place for electronics. Every single time a fuel injector fires or a spark plug ignites, or even when an electric motor spins up, it just screams electrical interference or noise into the entire system. Now, this noise, it's kind of like static on an old radio. And for the super delicate digital signals that control your engine, your brakes, and your airbags, that static can be absolutely disastrous. And that right there is the million-dollar question for automotive engineers. How do you make sure the command to deploy an airbag doesn't get totally garbled by the motor for the electric window? Well, the answer lies in two fundamentally different ways of sending a signal. Okay, so the first and, the most obvious approach is something called asymmetric signaling. It is by far the simplest way to get the job done, but as we're about to see, that simplicity, well, it comes at a pretty steep price. So here's the core idea. You've got one wire, and it's carrying your data. The computer on the other end, the receiver, measures the voltage on that single wire and compares it to a common reference point for the whole car, which we call ground. If the voltage is high, that's a 1. If it's low or 0, that's a 0. Simple enough, right? But its big weakness, its Achilles heel, is that it totally depends on that ground reference being perfectly 100% stable. To really get this, let's use an analogy. Imagine your signal is just a single person speaking on a stage, and the ground reference is the quiet floor of that stage. The audience, that's our receiver, is just listening to how loud that one speaker is compared to the quiet floor. Sounds pretty straightforward, until, the hecklers show up. And this is exactly where the problem starts. That electrical noise we talked about, it's like a heckler in the crowd just shouting over our poor speaker. It adds its own random voltage spikes right onto that single wire. So now, the receiver at the other end has no way to tell the difference between the original message and all that noise. The data gets corrupted, and the message is completely lost. So if that single wire is just too vulnerable, engineers obviously needed a much cleverer solution. Let's move on to the second approach, which is called symmetric signaling. And this one was designed from the ground up, specifically to fight and defeat noise. Now, this approach is a total game changer. Instead of just one data wire, we're going to use two. And here is the absolutely crucial point. The receiver no longer cares at all about the voltage of either wire compared to ground. All it cares about now is the difference in voltage between those two wires. Let's go back to our stage analogy for a second. With symmetric signaling, we now have two speakers on the stage. But here's the trick. When one shouts +5, the other one, at the exact same time, shouts -5. The receiver, our audience, isn't listening to either speaker by themselves. Nope. It's only listening for the difference between them, which in this case is a crystal clear 10. And this is its superpower. When that electrical heckler, the noise, starts shouting, it hits both wires, which are usually twisted together, at pretty much the same time and with the same intensity. So the receiver does some really simple math. It takes the voltage of wire A plus the noise, and then it subtracts the voltage of wire B plus the same noise. And what happens? The noise just cancels itself right out. The original difference between the two wires shines through perfectly clear. So that's the theory, which is pretty cool. But what does it actually mean for the car that you drive every single day? All right, let's put them head to head. Asymmetric signaling is simple. It uses one wire, but it's super vulnerable to noise. Symmetric is a bit more complex. It needs two wires, but its entire design is based on just ignoring noise, which makes it incredibly robust. It really is all about trading a little bit of simplicity for a huge, huge gain in reliability. And that's a core decision in automotive engineering, right? Balancing cost and complexity against absolutely bulletproof performance. And you'll actually find both types in your car right now. They're used in different communication networks, or buses, which are basically shared data highways. Asymmetric signaling, which you'll find in a system called the LIN bus, is perfect for simple, non-critical stuff like controlling your windows or mirrors, places where cost is a big factor. But for the absolutely critical high-speed networks that run your engine, your brakes, your safety systems, things like the CAN bus or FlexRay, only the noise-canceling power of symmetric signaling is good enough. So the crucial takeaway here is that this isn't just some academic exercise. As we barrel towards a future of self-driving cars, the integrity of these signals becomes everything. The car's eyes and its brain will be communicating over these exact same kinds of wires. Understanding this unseen battle against noise is fundamental to building a future we can literally trust our lives with. It really makes you wonder, what comes next?